Hi, my name is Cooper Nicholson, and welcome to my Physics 2211 Lab 1 report, Constant Velocity. The purpose of this lab is to show the real-world application of Newton's first and second laws and how they will affect the position update formula. To do this, an object with constant velocity is observed and its motion is recorded. The motion is then compared to a simulation to help investigate the relationship between velocity and force, along with predicted positions. A computational model, GlowScript, was provided as a way to compare theoretical motion to an observed object. The position update formula was also used, as the position would change by the same amount every second with constant velocity. The other fundamental principles in this lab are Newton's first and second laws. The first states that an object at constant velocity will stay at that velocity until it is acted upon by an external force. The second law describes the relationship between force mass and acceleration, or momentum over time. It can be modeled by the following equation. Based upon the data collected from the observed and computational models, there's almost a one-to-one match, showing that predicted position and observed are closely related. The graphs on the next slides will break down the comparison between the two models. However, there are some discrepancies that will be discussed later in the report. In accordance with Newton's first law, to achieve constant velocity, an object must be in motion with no external forces acting upon it. This means that the net force must be equal to zero, which, if applied to Newton's second law, would show that the acceleration is also equal to zero. This can be seen in the graph below, as velocity is a straight line across the x-axis, showing that it is unchanging and has a derivative of zero. With constant velocity, the change in position is then predictable, as it will always increase by the same amount. In the computational model, net force was put to zero, and the velocity was set to the mean of the average velocities observed on each frame of the experiment, or the line of best fit slope, which resulted in 1.24 meters per second in the positive x direction. The mass of the pool ball was found from an internet search, and the time of the while loop was changed to 0.867 to match the time of the observed. The direction of the velocity is also assumed to be positive, since the ball rolled from left to right and a normal coordinate system was used. As predicted by Newton's laws and the position update formula, the progression of the ball's position is a linear line with a constant slope. Each x value is increasing by the same amount, and regardless of time, the position could be accurately predicted. The coordinate system is slightly offset to account for where tracker observed that the ball started from. In the observed model, the system is a pool ball and the surroundings are everything else around it, including the pool table and camera. The camera was set up, then the pool ball was rolled across the table. After this, tracker was used to go frame by frame and plot the position of each point to create the graph below. While the line is not perfectly linear, it is a very close match to the predicted model. A comparison of the two graphs shows that they are both very similar, and while the simulation in orange is a perfect linear progression, the tracker in blue is not. Changes to the code. Each line of code was modified to make the simulation as close to the observed as possible. The initial ball position was changed to the starting coordinates of tracker, and the initial velocity was updated to the line of best fit slope. T was then altered to 0.067 and the same time as the observed ball, and delta t to 0.033 since tracker measures each frame at that rate. Finally, the while loop was updated to 0.867, and the final ball position was updated to make sure the simulation was moving at the correct positions. In the simulation, the ball moved slightly more distant, but at a slower velocity. This can be accounted for due to the assumptions made in the models. For there to be a constant motion, there must be zero net force, and while the computer can achieve this, it is very difficult in practice. The ball in the observed model was subject to net force even if for a second through friction and possible incline on the table, both of which would have caused a discrepancy between the predicted and what is observed. Primary sources of error would come from tracker, and while the ball was tracked multiple times, there can still be small errors, causing the measurement to not be 100% accurate. Another large source of error would be how the ball is tracked. The ball needed to be marked in the center of each frame, and while the sensor was estimated as best as possible, it is not entirely accurate as well. If the positive x and negative x directions were swapped, the graphs would change direction, but the relationship between the models would stay the same. The code would be altered as well to match the new observed, but velocity would swap signs and keep the same magnitude. This can be seen in the graphs below, as the amount traveled is the same and the slope of both lines is the same, the second is just negative. While constant velocity does result in zero net force, this does not mean that there are zero net forces acting on the ball or that we can assume that it is so. If two forces with opposite signs but same magnitude oppose each other on the same object, there would be a zero net force despite having two forces affecting the object. Further demonstration is shown by the figure below. If two people were to push the box on opposite sides with the same force, there would be forces acting on the box, but the net force would be equal to 0. In conclusion, the analysis of the ball rolling over a short period of time where constant velocity is observed is almost identical to the distance and velocity predicted by a computational model. Thank you.